Thank you, Sarah. And I'm back with voice. And all right, so Bayesian inference for proportion. And so like I said, this is a relatively long chapter, but you will see that some of the details of the calculation that we did in the all-nighter example, we're going to dig into a little bit more here. And if you also remember for that all-nighter example, when we did that, I mentioned that there's a drawback of using a discrete prior, because if some values are not, like some possible values of the success probability P are not expressed in the prior distribution, in the posterior it won't show up either, because it's always going to be 0. Okay, so we're going to see one way to make it work is to, instead of using a discrete priors, we're going to use a continuous prior, and we're going to introduce the beta distribution. And then finally, I will show you how to update the beta prior to its posterior. And then, of course, how to do Bayesian inference with this continuous prior. So I think this week and maybe also Wednesday next week, we'll use most of the time talking about this chapter. And I will use a motivating example of Tokyo Express consumer dining preference. And this is a Japanese restaurant run by Chinese, by the way, on Lagrange Avenue, 10 to 15 minutes walk from Vassar. And suppose the restaurant owner wants to improve the business even more, especially for dinner. And by the way, I know they only do takeout at this point, but let's just assume this works in the way that we thought it would. And so the plan is, let's just say the owner wants to conduct a survey by asking their customers, what is your favorite day to eat out for dinner? Okay, so they want to get this information from the customers, and then maybe they can shift a little bit of their work shifts and all of the plans, so they can, if Friday is really popular, they can have more people and servers helping out that day. Okay, so so at the end of the day, the owner wants to find out how popular is the choice of Friday, and you can see that, of course, you can ask the question is, what is your favorite day to eat out for dinner? And people might choose Monday through Sunday, so it's going to be like a categorical response, right? Different choices. But if we only focus on Friday, we can turn it into a binary outcome. It's Friday or not Friday. Okay, so we're simplifying everything, and the goal is trying to just find out how popular Friday is. Okay, so that's the motivating example, and I'm going to show you how to do discrete priors, which is very similar to the all-nighter example, like I said. But we'll get into the detail of how the update is doing in detail this time. So just to refresh our memory, we talked about 3 general steps before for doing Bayesian inference. You have your step 1 to talk about the prior. This is trying to express the opinion about the location of the proportion. So P is the proportion parameter of interest. So it's going to be where the P value is going to be, right? And how likely we think each value is going to be, just like what we did in the all-nighter example. The step 2 is what we call, we're going to take the sample or take a sample and record the observed proportion of preferring Friday. And we call that as the data, or later we're going to introduce the concept of likelihood, and that will be the likelihood function part in step 2. Step 3 is use Bayes' rule to update the previous opinion about P given the new information, and that's what we call the posterior. Yeah, you can see that I use the word update as well as sharpen. Okay, so the sharpen you will see later as well is that you might have a very vague prior to start with. Okay, like I think maybe P can be anywhere between 0 and 1. And then all of a sudden with the data coming in and with my likelihood function, with the Bayes rule working, I will be able to not only update my understanding of P from the prior to the posterior, but also make it more refined. Okay, so you'll see that we become more confident about certain values given the data that we're going to see. So we're going to see that example coming up as well. So these are the 3 general steps. This is going to reoccur many times, as you will see throughout the semester. Right now, we're dealing with the proportion case and then with discrete priors. And I should also say later, you're going to see that this Bayes rule is the discrete Bayes rule that we talked about last time. Okay, we're doing a summation because we're only going to actually give discrete priors coming up. So hopefully this will become a little bit more in context. So Bayesian inference with discrete priors, like I said, we have to, first of all, come up with priors, and we're going to list a finite number of possible values for the proportion P, and we're going to assign the probability for each of them. So only if you complete the list of possible numbers, as well as the list of probability to each of them, you are completing the prior distribution. Okay, it is the distribution that is about the numbers, the values, as well as the assigned probability. That's step 1. Step 2 is we're gonna take the data and you're gonna see the binomial distribution as a review as well. Okay, we're gonna say that for like say whether people are going to say yes or no to whether Friday is their best choice, it's actually a binomial experiment, okay? Because people can either say yes or no, and we're going to have a binomial distribution, the expression and everything going on into the data and the likelihood part. And lastly, we're going to use the discrete version of the Bayes rule. So you're going to see that we're going to use the summation sign instead of the integration, because this is a discrete case. And eventually we're able to get the posterior probability of each specified possible values of P. Okay, so that's the overview here. And hopefully we get to see some of the details and then a little bit more specific than the all-nighter example. Consider percentage of customer's choice is Friday. Okay, so that's the unknown P of interest. Before giving out the survey, and by the way, people will always try to come up with the prior without seeing any data. Okay, that is trying not to interfere the inference using the data before you see it, because you want to come up with a prior that really reflect what you believe before seeing it. Okay, so let's consider the possible values of P, and also we should try to assign probability for each of the value of P. Suppose, again, this is a toy example of, we have 6 possible values. I'm just saying that it would be 0.3, 0.4 up to 0.8. Okay, I have 6 different values. It's discrete because I have finite number of possible values. And let's just say the owner believes that some values are more likely than the other ones. Suppose they want a prior like this. So if you remember, we're going to use pi to represent the prior. Okay, and then here I just put an owner just to reflect that this is the owner's prior. Okay. And then pi is usually stands for the prior distribution, and then the parameter is P over here. So what this is saying, as you can see, is that the owner thinks 0.5 and 0.6 are more likely or twice as likely as the other 4. Okay, so this is what this prior is about. My exercise for you to think through and then talk to your neighbors is, do you think this prior is reasonable? Of course, you can disagree of how you think the values of P and how likely they are should be, but maybe let's double check that this is a legitimate prior, I should say, to start with. Okay. My hint here is that there are 3 axioms or probabilities. They're all disjoint, right? Do they add up to 1? That kind of stuff. So take a moment to think through and reflect and talk to neighbors, and then we will resume from there. All right, in the interest of time, let's just say for this prior, I guess we do have 6 different values, right? And then we have 6 different, I should say 6 associated probabilities. The 6 different possible values of P, they're disjoint from each other, right? Because they're different. And then also the probabilities of them, they add up to 1. So that's the main thing we should be checking. But I also overheard people talking, well, it could be a little bit complicated or not as easy to conceptualize what this value of P itself. Okay, so P again is the proportion of people going to say Friday. Okay, and we're just saying that. So imagine this proportion can be anything between 0 and 1. For now, we're simplifying things to make what we call a discrete prior, because we're only saying that, well, there are only 6 possible values out there, and there are 0.3, 0.4 up to 0.8. Okay, and specifically, we're just saying that the total express owner thinks the middle one, 0.5 and 0.6, are twice as likely. But it could be that another person come along and saying that I think it's much more likely for people to go out on Friday. So I would place much more higher probability for like 0.7, 0.8. And you can do that. And as long as they add up to 1, you're good to go. Okay. All right. So with that in mind, I want to end this part with one last slide of using R and R Studio Express and plot the prior. Okay. So this is using ggplot. Okay, and like I said, on Moodle, I also posted a markdown file, including all of the R code itself. Okay, so you should be able to play with it afterwards if this is what you want to give it a try. But basically what we're doing is that we're creating a data frame over here. Okay, and you can see that the value of P is initialized as a sequence from 0.3 to 0.8, and the increment is 0.1. Okay, and also I have, or we have this, so that's the column of P. We also have a column called prior is in the data frame, and we just like typed out the 6 different probabilities that we just wrote earlier. Okay, and with all that, you're able to use ggplot to do a bar plot over here, and we have your x-axis to be the P, the probability, the proportion itself, and y is the prior. So you can see that to visualize it, we exactly seen that the middle two are twice as likely as the other four. So of course you can have other ones, like I said, like much more higher probability for 0.7, 0.8. So you're gonna see something a little bit more less skewed, if that is what you want. Here, this is example of a symmetric. And in particular, we needed to make sure that they satisfy the 3 axioms of probability. Okay, all right, so with that in mind, I think we should end here.